Good morning, sir.
Good morning. Okay, so continuing with our discussion, screen is visible? Screen is visible or not?
Yes, sir. Yes, sir.
Okay,
Visible.
so quickly discussing when there is a hump, the specific energy changes from E1 to E1 dash. Positive hump, the vertical PP dash, the vertical at E1 PP dash. If there is a positive arm, will move towards left, and if it is a drop or negative arm, then it will move towards right. This specific energy diagram itself explains, this specific energy diagram itself explains what happens. Okay, so uh, uh, when there is a positive harm and the flow is subcritical, then downstream of the hump, upstream whatever will be the depth, that will go on decreasing, as you can see from here. Flow depth measured from the bottom, okay, that will be decreasing. So nu y dash will be less than y. Y dash will be less than y. Okay. Now, if it is opposite, that is delta z is negative, then you move up in the specific energy diagram for subcritical flow and y dash is greater than y. Okay. In the supercritical flow, it is the reverse. Y dash is greater than y when delta z is positive. Okay. You move towards left and you see from the lower limb that the depth y is increasing, and as you drop, you see that the depth y is decreasing. So this is the summary. But then what happens when there is or say it is reaching the maximum? It is reaching the maximum. Okay, or we can say delta z maximum. Whatever specific energy you'll have. Okay, so the specific minimum specific energy EC, if you deduct from E1, then that will be the maximum hump height, delta Zm. Okay, fine. Now, what happens when when delta Z when delta Z is greater than delta Zm. So this part we'll discuss now. When delta Z is greater than delta Zm. Fine. So now downstream specific energy will be as per our deduction E1 dash minus delta Z equal to E1 dash equal to E1 minus delta Z. Now that will be less than EC. But at the discharge, the particular discharge which is under consideration, this is the minimum specific energy. Okay, so downstream just EC will be maintained, and whatever the shortfall that will be provided by increase in the specific energy upstream. So in this case, your E downstream will be equal to EC. Okay, E downstream will be equal to EC. Fine. And E upstream is modified to E dash which is equal to okay. Just a minute. It got hanged. The subcritical flow, and the graph shows the variation of Y1 and Y2 in subcritical flow over a hump. So the delta Z from 0 goes on increasing up to delta Zm. In that case, the upper curve is for depth Y1 and the lower one is for depth Y2. Okay, the upper curve is for depth Y1 and the lower curve is for depth Y2. And what you can see that when Z increases from 0 to delta Zm, the upstream depth Y1 is not changing. Upstream depth y1 is not changing, and it is remaining. You can see the horizontal line at the parallel line to the x-axis, and whereas the depth, whereas the downstream depth y2 is falling continuously, and from y1 it falls exactly up to yc when delta z is equal to delta zm. And after that, the downstream depth remain same at yc, but to provide additional specific energy, the vertical now will move towards right, because it is subcritical flow. Because it is subcritical flow, you will have the vertical moving towards right, resulting y1 dash new y1 will be greater than y1, and this will move upward like this. Okay. So the first case up to this, y1 is constant and y2 is falling up to yc. Okay, exactly at delta zm, y2 equal to yc and y1 equal to y1, and the flow is critical downstream. And the situation delta z greater than delta zm, you will have downstream depth remain constant. Downstream depth remain constant at yc, and upstream depth will be modified to y1 dash to provide the additional specific energy required. Okay. So coming to, this is for the subcritical flow. Coming to the supercritical flow. Coming to the supercritical flow. Okay, supercritical flow over a ham. Now, first case, if delta z is less than delta zm, up to that, the flow depth y1 will remain constant. Flow depth y1 will remain constant, but y2 will go on increasing from p double dash to r double dash up to c. So y2 will go on increasing up to c, and then yc. Then further increase in delta z. So delta z greater than delta zm, your y2 e2 will be maintained at ec, and e1 will be e1 dash, thereby which will be increasing, means the vertical will move towards right. So what happens when the vertical move towards right? The flow depth y1 will be now decreasing, as you can see, to provide additional specific energy in the supercritical flow. In the subcritical flow, it was increasing. Okay, so the curve was upward. Now you will see the curve for y1 remaining constant up to delta zm, and it will be increasing. Y2 will be increasing up to yc, because it is supercritical flow. You can see y1 is less than yc. Okay, So this is your YC. This is your YC. Okay. Y1 less than YC means it is supercritical flow. Y1 less than YC means it is supercritical flow. And so here this is increasing, and then from here onwards, when we move towards right in the horizontal axis, where delta Z is greater than delta Zm, Y1 dash will be lowering to provide additional specific energy. So you see the line is falling, and Y2 will remain constant YC. Okay, so basically, if I would like to plot this, okay, you are asked to plot. You are asked to plot the variation of Y1 and Y2 in supercritical flow. Y1 and Y2 means the upstream depth and the downstream, the pre-hump depth and the post-hump depth in supercritical flow over a hump. Okay, supercritical flow over a hump, and that is you have to explain this. Okay, the explanation can be done from a suitable drawing a suitable specific energy diagram. Okay, drawing a suitable specific energy diagram, and then going for this plotting this. Fine, you can as well. You can this is for the supercritical flow, and you can as well discuss the same for the subcritical flow. Okay, from the same specific energy diagram. Fine. So these are the variation of hump. Okay. Quickly do a is done by okay. Try to derive this expression in a rectangular channel so that the maximum hump height is given by this. to compute EC, then this is 1.5 times this. Okay, that is what EC is. And what you get is 1.298 meter. Okay, 1.298 meter. So what is E2 now? If I write delta Z M, if I write delta Z M, okay, delta Zm is equal to 1.644 minus 1.298. Okay, and that is 0.346. 0.346 meter. 0.346 meter. Okay, which is less than 0.50 meter. Okay, which is less than 0.50 meter, because if I'm providing a hump, if I'm providing a hump of 50 centimeter, it is going beyond the delta Zm value. So now your at the downstream section, E2 will be equal to EC. Okay, E2 will be equal to EC. And what about E1 dash? What about E1 dash? E1 dash will now become EC plus delta Z, isn't it? EC plus delta Z. And that is what is equal to 1.798 meter. 1.798 meter. Okay, and now you can compute what is E1 dash. Okay, what is E1 dash? So send your network quality is becoming bad. So we'll stop in 2-3 minutes. Solve for Y1 dash. Solve for Y1 dash for this 1.798 meter for this. Solve for Y1 dash. Okay, so send this answer again in your WhatsApp. Okay, whatever we discussed, that can come in exam like this. Discuss the channel transition. This I took from the question paper, mid-semester and semester question paper. discuss the channel transition with a hum with the help of a specific energy diagram and variation of pre-hum depth Y1 and post-hum depth Y2 in subcritical as well as supercritical flow. So all that we discussed, that will be, you can put it in 2-3 pages for this long question. Okay, maybe carrying 7-8 marks out of 10 marks. This may not be a 10 marks question. With this, there may be a small 2-3 marks question, making it a 10 mark question, the way you get it in your mid-sem and sem. Okay, and the similar thing will be for the width constriction. Explain the channel transition with a change in width with the help of specific energy diagram and draw a neat sketch showing variation of pre-constriction depth Y1 and post-constriction depth Y2 in a subcritical as well as supercritical flow. So there is a constriction in the width. Okay, so this is change in width. Okay, so this is change in width, and we have to see that, like, for the change in width, how subcritical flow and supercritical flow, Y1 and Y2 variation, that we'll see in the next class. Okay, that's all for this class. Fine. So should we stop now?
Yes, sir. Yes, sir. We have class, sir. Now.
Okay. So
Okay.
we have next class on Monday, and Monday it is not 11 o'clock. It is not 11 o'clock. Okay. Next class Monday 12 to 1. Fine.
Yes, sir. Yes, sir.
Okay. Bye. Bye.
Yes, sir.